Hi guys, Mr. Rocco here. I hope you had a good Thanksgiving. We're going to pick up where we left off last week. We covered Kepler's first law, so we're going to cover in this video Kepler's second law, which is called the law of equal areas. So this is just a review of the first law. So Kepler in his first law said all planets travel in elliptical shaped orbits. And again, an ellipse is a flattened circle, you could call it, or an oval. It has two center points called foci. So there's your two foci. The distance across the middle, again, is called the major axis. So these two dots are your foci, and the distance across is called the major axis, which is like diameter. Again, you can't call it diameter because it's not a circle, it's an ellipse. So because all planets travel in an elliptical shaped orbit, where a planet does not stay the same distance away from the sun, and that was also part of Kepler's first law. So the sun, I'll put an S, is at this foci. There'd be another foci over here, which has nothing. It's just to center, to balance out the shape of the ellipse. So because we travel in elliptical orbits, and the sun being at one of these foci, the distance between a planet and the sun is going to change. If we were in a perfect circle, that wouldn't be the case. Our distance would always be the same no matter what day, month, etc. But because we do change our distance, we have two new terms here. When the Earth is furthest from the sun, furthest away, that's called aphelion, A-P-H-E-L-I-O-N. Again, helio, you should recall that means sun. That's from the Greek word helios, right? We had two models of the solar system. One was called geocentric and one was called heliocentric. So helio has to do with sun, and then the AP, the way I try to get students to remember that is just think A, away. So when we're furthest away from the sun, we are at aphelion. That's going to put us at 95 million miles. When the Earth is at its closest distance to the sun, that's called perihelion. P-E-R-I-H-E-L-I-O-N. Again, helio meaning sun, and this time peri means close. So perihelion, close to the sun. The way I try to get students to think about peri is on a submarine. Right? If you're talking about the U.S. Navy, my wife has a cousin. He's in the U.S. Navy, and he actually is a submariner. He goes out of, I think, Seattle, Washington. But anyway, the scope that comes out of the water, right, when the submarine is underwater, and then it shoots the scope out to look around what's going on at the surface, is called a periscope, right, a periscope. So that's P-E-R-I. There's that peri, and scope means to look. Right, like microscope means to look at something small, or telescope means to look at something beyond, right, the stars, the planets. So peri means close, and then helio means sun. And that's when we're 90 million miles. So if you take the average between 90 and 95, right, that's 92.5, which rounds up to 93. So a lot of your websites and textbooks will say that the sun's distance, or excuse me, the Earth's distance from the sun is 93 million. That's the average, right, if you round it to the 10th. But we are closer, it's called perihelion, and we're further, it's called aphelion. And so here's the definitions right here. Aphelion, again, think A, away, when we're furthest from the sun. That is actually not common sense. So we haven't done seasons yet. We'll be doing that probably next week. Seasons have nothing to do with the distance we are from the sun. Seasons have to do with our revolution going around the sun and the tilt of our axis, which is at a 23.5 degree tilt. So we're actually we're actually further from the sun in the summer, right? July 4th, into our Independence Day, is summertime. That's when we're further from the sun. We're actually right now, it's late November going into December. We're actually getting closer to the sun right now. We're approaching perihelion. So peri means close, and then again helio, sun. We reach that right around New Year's, just after New Year. January 2nd is when we reach our closest distance to the sun. Even though it's winter, For us, it's our closest point to the sun. So it's not common sense when it comes to distance and seasons. That's all, again, tilt. But these are two terms that you need to know. So aphelion, further from the sun, away from the sun, July 4th. Perihelion, closest to the sun, January 2nd. Now, the moon also travels in a slightly elliptical orbit. So let's say this is the Earth. And again, I'm drawing with a mouse, so you have to apologize. The moon goes around the Earth in an elliptical orbit. And so the moon is also going to be slightly closer to us at certain times in the month, and other times in the month further away. And the same things apply here. So when the moon is further away, again, A for away, it's also called, there's the AP, apogee. The GEE comes from GEO, which means Earth, right? Geocentric model was Earth in the middle. So apogee is when a satellite, in our case the moon is our natural satellite, is further from the Earth. And then there's that peri again. Perigee is when the moon is closest to the Earth. That creates what they call, and this is the new thing you'll hear. Well, it's not new, but it's new when it comes to the media. They like to put this term out there, supermoon. What is a supermoon? A supermoon is a full moon, but it also happens to coincide when the moon is at perigee, which is going to happen occasionally. Not every full moon is a supermoon. I believe Monday night, November 30th, is a full moon, but I don't think it's a supermoon. I'll have to double check. I don't think it is. But anyway, so if it happens to be a full moon and the moon is at its closest point to the Earth, it's going to look bigger. They call that a supermoon. So apogee, again, A, away, furthest from the Earth, and perigee, closest to the Earth. So here's your, actually you can see in this picture up here on the left, the difference in size. There's a pretty good size difference between the two. This would be what the moon would look like in the sky if it was at perigee. So this would be your supermoon, and this would be if you had an apogee full moon. As you can see, much, much smaller. Big difference there. And you can see down here, the difference between apogee and perigee is about 30,000 miles, which is quite a big difference. The moon on its average is about 240,000 miles away. So you're talking, 1/8 difference there, 30,000 miles. So here it says the most recent full supermoon occurred January. There was one January of 2018, January 31st. There was another one December 22nd, 2018. So we had two supermoons in 2018, beginning of the year in January and the end of the year December. The closest supermoon was November of 2016. That was the closest since January of 1948. We won't have that close of a moon until November of 2034. So we got to wait about 14 more years before we have another really big supermoon. But you can see this also shows the difference here. Here was a supermoon on March of 2011 on the right. This one was December 2010 on the left. And you can see there's a pretty decent sized difference there between full moons when it's apogee versus perigee. All right, so this is Kepler's law in terms of what he put it in terms of, and then I'm going to put it in easier terms. It was called the equal areas law. And so what he said was each planet orbits the sun in a way that an imaginary line connecting it to the sun will sweep or cover equal area of space in an equal time period. And so what Kepler was saying, every month, right, we have 12 months in a year, every month the Earth has to sweep or cover the same amount of area of space. And so let's show a picture, maybe that'll make more sense. So here's the sun at one of the foci. I'll put an S. This would be when we're closest to the sun. And again, we're closer. That was called perihelion, and that was January. Right, January 2nd. So I'll put Jan. There's January. Way out here is when we're furthest from the sun. That was aphelion, and that's going to be July. So what Kepler is saying is, in the month of January, we're going around the sun, if we're looking from above like this, counterclockwise. So this point right here would be New Year's Day, January, or beginning of January. This point over here would be the end of January, January 31st. So what Kepler is trying to say is we have to cover the same amount of area in January. This green section over here has to be equal to this long green area over here in July. This area here has to equal this area here. So what he's saying is that's the equal areas law. We have to move at a different speed. So if we have to cover this area here in the month of January, and we have to cover this area out here in the month of July because they're equal, notice how much, this is our orbit, we have to move. So in January, we have to go from this point all the way around to here, to this point in the month of January. That's a pretty big distance. Compared to July, when we're further away, we don't have as far to travel. We only have to go from here to here. If I was to measure this line over here on the left and this arc over here on the right, you can see this line is much longer. What does that mean? We have to do it in the same amount of time, right? Equal time, meaning same month. That means this line being longer, we have to move faster. So we're going a lot faster when we are closer to the sun. Which right away you could probably think why that happens, right? Why would we move faster when we're closer to the sun? What's going to be stronger between the Earth and the sun when we're closer, right? And hopefully you're thinking gravity, right? The gravitational pull, which is affected by distance, is what creates that that faster velocity. So we speed up when we're closer to the sun, and over here, when we're much further from the sun, we slow down. But what he's talking about, Kepler, is equal areas. We have to cover this area here in the month of January, and we have to cover this area here in the month of July. These areas are equal. Even though this is a short, fat area, and this is a long, skinny area, they're the same. And that was his whole idea behind equal areas. We speed up when we're closer, we slow down when we're further away. But the problem with Kepler was he couldn't explain gravity. He didn't know about gravity, but as we know today. This animation, where is it? Let me show you that. So this is going to show, now this is exaggerated, but this is showing you over here on the left is aphelion, and over here on the right is perihelion. So again, we're further away when we're out here. Notice we slow down. This is Earth traveling in its orbit. And then when we get closer to the sun, we increase our speed. So as we go from aphelion to perihelion, so you're talking 6 months. So this is July. So August, September, October, November, December, January. So for 6 months, we increase our velocity slowly until we get to our fastest velocity here. Then for the other 6 months, once we pass January, we go February, March, April, May, June, July. 6 months we're slowing down. So we have 6 months of increasing speed. Then we hit our fastest point here, and then 6 months of decreasing speed. And then we just keep doing that, right? It's a cycle, just like our seasons are a cycle. So we speed up, and then we slow down. And again, Kepler could not explain why. He did not know about gravity. Newton comes along, right? Isaac Newton, and it says here, the Philosophiae, Naturalis Principia Mathematica. That's a big tongue twister there, but that's the book that Newton wrote. He wrote that book. It took him 2 years. It was published in 1687. It was the culmination of 20 years of thinking. So this was a 20-year project. It took him 2 years, Newton, to write the book. It comes out in 1687. Kepler, unfortunately, died in 1630. So he died about 50 something years before the book came out. So again, Kepler didn't know. People would ask him, okay, I know what you're saying, right? We speed up when we're closer, we slow down when we're further, but why? He couldn't explain why. He didn't know about the force of gravity, which is affected by two things, mass and distance. It's a direct relationship with mass, right? If I have two objects, let's say these are two objects here, A and B, there's going to be some gravity between them. But if I take these two objects and make one of them bigger, let's say that's A, and now B looks like this, right? B's on steroids. And now B is much bigger. The gravitational pull between them is going to be much stronger because I increase the mass of one of the planets. Now let's say I have two planets, and I'll do up here. Let's say this is A and this is B, and they're so many miles apart. All right, there's gravity between them. But now over here, I'm going to have A and I'm going to put B way out here, right? So when I increase the distance, I decrease the gravity. That's an inverse relationship. So as the distance increases, the gravity decreases, right? That's why we slow down when we're further from the sun, and we speed up when we're closer to the sun. But again, Newton comes out with this book in 1687. Kepler, like I said, died many, many decades earlier, not being able to explain the whole idea behind gravity. So Kepler again says every month we have to cover the same amount of area, but really the law in more simple terms is the closer a planet is, Earth or any other planet, Mars, is to the sun, the faster, the greater its velocity due to gravity, right? And then the further a planet is from the sun, right, the lesser, the slower its velocity, again, due to less gravitational pull. There is a way you can actually check this. The calendar is the way you can do it. If you took, let me go back just for 1 second. If you took, again, this out here is July. So that's our summer, right? And over here is January. That's our winter. If you add up all the days of, let's see, not fall, spring and summer. If you took a calendar, started on the first day of spring and go all the way to the last day of summer, and then over here, add up all the days of fall plus winter. Since we are going faster in the fall and the winter, December, January, etc., there's actually less days in the fall-winter seasons for us. I believe, don't quote me, I want to say it's about 10 days less. So we actually have 10 less days of fall plus winter. We have 10 extra days of spring plus summer. And that's this whole speeding up, slowing down idea with Kepler's second law. But yeah, if you add up, that calendar is the one way you can actually see that it's doing it. You don't feel it. It's not like right now you're saying, "Oh, Mr. Rocco, I could tell we must be moving a lot quicker. We're heading toward the holidays, and we're heading toward New Year's, and boy, I'm getting a crick in my neck. We must be getting whiplash. We're moving a lot quicker." No student has ever come up to me in 20 plus years and ever said that to me. "Oh, I could tell we're moving faster. My neck hurts. Every time I wake up in the morning in the wintertime, it must be accelerating." Nobody's ever come up to me to tell me that. You can't really, you're not going to notice it. It's a slight shift in the speed. It's a very slight variation. It's not much, but it does exist. So that's all this whole idea behind Kepler's second law. We speed up when we're closer. We slow down when we're further away. And I think that is it. Yes. So I will post this video on Canvas. Watch the whole thing. Pause it, rewind it, go back, make sure you understand aphelion, perihelion, apogee, perigee. And I will talk to you soon.